I'm Ashley Hammond. I'm a paleoanthropologist, in addition to being the chair of anthropology. And so that means I work on the fossil record for ape and human evolution. And tonight I have the great privilege to introduce someone that I get to call a colleague, Dr. Kevin Uno. And I'm kind of in an unusual spot because I feel like no matter what I say about Kevin, I will not do him justice. He's really at the forefront of his field. Kevin uses isotopic data, which you'll hear more about tonight, and he uses isotopic data to characterize paleoclimate, so climate in the past. And he really is at the forefront of paleoecological questions and techniques that use this kind of data to understand a range of topics, so dietary ecology, vegetation, and climate in the past. I'm going to lay off on all of Kevin's really wonderful scientific attributes and also give an acknowledgement to the Leakey Foundation. The Leakey Foundation is co-hosting this event tonight. They do so annually. They have an annual SciCafe, sort of in the spirit of the kind of work that they fund, which is typically things related to human evolution and primatology. So the Leakey Foundation, as I said, they're a nonprofit that's dedicated to supporting human origins research all around the globe and to disseminating that research. So if you want to learn more about them and the work that they do, you can go to leakeyfoundation.org. And without further ado, I will now introduce Dr. Kevin Uno.
Good evening, everyone. And as Meg and Ashley said, thank you for venturing out into the rain to come tonight. So I'm going to start with the question. Who controls the climate in your home? Is there a constant battle between you and your partner or your kids turning the heat up or down? In our apartment in New York, none of us are in charge. It's the landlord. But climate control in our home, it makes us comfortable and it makes us safe during periods of extreme cold, heat, or tonight, wet. And even though it's a luxury, it's something we've all sort of come to expect. But the world wasn't always like this for humans. So our story, the story of humans, began about 2.5 million years ago with the advent of our genus Homo in Africa. Homo sapiens, our species, evolved a mere 300,000 years ago. And for most of our history on Earth, we didn't have climate control or even dwellings, and we were therefore at the mercy of the Earth's ever-changing and fluctuating climate. So how did our early ancestors survive the tumultuous swings in climate? Ooh, and why do you see my desktop? For those millions of years before we had insulated homes and offices that we commute to in climate-controlled subways, buses, and cars. The question is, in essence, how did we as humans survive in this ever-fluctuating climate? And the answer is, we adapted. My background is in earth science, and so I'm going to take us in the Wayback Machine. And what we're going to look at here is the last 66 million years of atmospheric CO2, which is in the black line, and the levels are on the left, and temperature, which is in the climate stripes you'll see here, where warmer temperatures are in reds and cooler temperatures in blues. And these are relative to the pre-industrial global mean surface temperature, the average temperature on Earth. And what you can see is, and I'm choosing 66 million years because this is the end of the dinosaurs and the beginning of mammals, the rise of mammals, which is our group, okay? And you can see in the past, the Earth has been much, much hotter. But if we think about the beginning of our group, the hominins, that came a mere 7 million years ago or so, shown here. So our entire history on Earth, okay, has been in a much cooler and lower CO2 time period. And as I mentioned, our genus Homo is about 2.5 million years, so even further along. And then on the far right, if you can see, let me get out of the way, there's a box that shows the last 800,000 years or so. So I'm going to start moving us closer to today, and then here is CO2 at the end of 2023. Quite high, 420 parts per million or something. And in this paper by my colleague and friend Bärbel Hanisch and colleagues, what they noted in this reconstruction of 66 million years of climate and CO2 was that we have not seen CO2 this high for probably the last 14 million years. So we're really in an unprecedented time in terms of the composition of the atmosphere. And this is how we sort of broke the Earth's thermostat. So now we're going to zoom forward and just look at the last 800,000 years, okay? And it's 800,000 years because this is the most record we can get from the ice cores, okay? So we actually measure CO2 in the bubbles, and that's shown in blue. And you can see just as your thermostat clicks on and off, the Earth's CO2 has moved between about 180 and 280 parts per million over the last 800,000 years of this record, and probably going back about 3 million years in the Pleistocene. The other thing to note is that temperature tightly follows CO2, since it's a greenhouse gas. And so this has been the way the Earth has regulated over the last 800,000 years through these glacial and interglacial cycles. And the earliest Homo sapien is about 300,000 years. So this is the world we originated, evolved in. This is the Industrial Revolution right here. This is the last 200 years or so compressed over an 800,000 year record. And you can see we're out of the range of the last 800,000 years, and I showed on the last slide, really the last 14 million years. So since the Industrial Revolution, our need to control our environment to suit our comfort, we now realize, has come at a great cost to the environment, and ironically now poses the greatest threat to our species that we've ever faced. And yet it's this ability to adapt, not our ability to control, which will be key to our survival in the face of anthropogenic or human-induced climate change, which started decades ago. And so now I'm combining temperature on the y-axis here, and then these climate stripes showing over the last 170 years or so how temperature has increased just in our lifetimes. And it really starts somewhere back in the 70s. And today we see rising temperatures. 2023 is not on here, but it's the hottest on record. It's somewhere there. And with these rising temperatures, mega droughts, melting ice sheets, rising sea level, and in the last few years, more frequent hurricanes and bigger, more destructive wildfires around the world. So what's at stake for humans in the face of climate change? From an evolutionary standpoint, it's the same for us as it is every other species. Adapt or go extinct. We can take a closer look at this rather dire option I just presented us with by going to East Africa. I'm taking us here because this is our ancestral home, our original neighborhood, if you will, where we evolved, along with all these other large mammals over millions of years and throughout climate fluctuations. It's a natural laboratory where we can evaluate how animals adapt or go extinct during periods of extreme climate fluctuation. And when we examine the fossil record, it turns out the average species duration for a large mammal from East Africa is about 1.3 million years. So from origination to extinction, the average species gets 1.3 million years. That's not long when you consider the Earth is 4.56 billion years old. And it's not long if you consider other species like the horseshoe crab. Their distant relatives evolved more than 400 million years ago, and the ones you see on the beaches today look essentially the same as they did during the Jurassic period 150 million years ago. So the horseshoe crab sets the bar for species longevity. Let's now look at us, Homo sapiens, again. We are a mere 300,000 years old. When I look at the state of the planet today, I wonder, are we even going to make it as an average species and finish out our allotted 1.3 million years? Or will we go extinct before then and end up as sort of a subpar species? I mean, humans subpar? Come on. Which species went to the moon? Not the horseshoe crab. We've been down to the bottom of the Marianas Trench, 7 miles below the sea surface. We've built skyscrapers 10 times taller than the tallest trees on Earth. We've built pocket-sized computers that recognize our face when we look at them. I mean, we've made some pretty amazing things. We control the climate in our homes down to the degree. And maybe my favorite, which I discovered while living in Japan, we created the Toto toilet seat, which opens when you enter, closes when you leave, and even has a heated toilet seat. Talk about the ultimate in climate control. The point is, we've created a lot of amazing things, and as a scientist, I've come to realize that these technical feats are not the hallmark of humans. Our real accomplishment is our adaptability. And since the beginning, we've been forced to adapt to the changing climate and environmental conditions. So what did that actually mean for early humans on the landscape? It meant that we had to find ways to find food resources, find water resources. We had to evade predators on the landscape, giant lions that were much bigger than the extant lions today. We had to figure out how to bear children and raise them, okay? And eventually, we came up with language that allowed us to work in groups to hunt or gather, or to share stories and build a collective knowledge. And then when we left Africa to colder climates in Eurasia, we needed to adapt. We found ways to make clothing, build shelters, and expand across the globe quite rapidly. So how do we know all these things about our past? Well, one of the things we know for certain is that diet is a key indicator of how well a species can adapt. And Charles Darwin, this wasn't his go-to saying, but he did believe that diet matters. And what he observed as he was writing Origin of the Species was that species that could adapt to their feeding habits or diet preferences were more likely to survive and reproduce. So why should we study diet? Well, it turns out in the natural world, animals interact most with their environment while they're feeding. So there's a lot to learn and understand just from knowing something about diet. With respect to humans, we can begin to ask questions like, did diet lead to our big brains? Diet informs us about the ancient habitats that our ancestors occupied. And if we know diets of multiple species in an ecosystem, we can start to understand who was competing with who for resources, so sort of niche breadth and overlapping of niches within that environment. And I'm going to dive a little deep into the science here with teeth, because they provide us a record of what animals ate in the past. And so to do that, we go to the fossil record. And since this is a Leakey Foundation-sponsored talk, I thought I'd dig out an old photo of Mary Leakey, who led the excavations at Olduvai Gorge for decades. And her partner, Louis Leakey, and I'm pretty sure this is their son, Richard, and they had a pair of Dalmatians with them. And Mary's many years of work at Olduvai produced things like this. This is, those of us in this field know them by species names and numbers. This is OH5, that's the specimen number, but it's a type of hominin we call Paranthropus boisei. It's about 1.8 million years old, and she discovered this in 1959. And this has been going on for like a century. Teams going out in the hot sun, digging for fossils, finding them, identifying, describing them. And here's a more recent paleontologist, my colleague Isaiah Nengo, who just passed away, sadly, a couple years ago. And he's the first Kenyan to get a PhD in anthropology at Harvard in the 90s. And about 10 years ago, discovered this infant cranium from a fossil ape known as Alesi, that's in just absolutely beautiful condition, and it's changed the way we think about this time period, the Middle Miocene in Africa. So these are the teams, the people doing all the work over literally a century that allow us to explore this deep, deep fossil record. But the fossil record is actually quite incomplete. And this is the most technical slide of the talk. There's an easier version coming next if you have a drink in your hand. And what I want to say about the fossil record being incomplete is, let's take a hypothetical hominin in orange, and their range is outlined here, moving through time. There's time step 1, 2, 3, 4. And then we have fossil sites. Fossil sites are where we get a snapshot, a window into the past, where ancient sediments are exposed. And the true range of this hominin in time and space in these different southeast, central, and north parts of Africa are shown here. But sometimes we have this range, but there's no fossils here. That's why these dots are open. And the fossiliferous sediments are actually up here. So there's no record. This is the actual range, and this is what we as scientists observe. So anytime we have a hominin fossil and some origination and extinction, we know that it's just an estimate probably, because we don't have the entire record, the whole history of the Earth, okay? So the easy version is the drunkard search, okay? And that is that the drunkard always looks under the lamppost where it's lit when he drops his keys. And so the lit area for us is the areas in which we find sediments that host fossils. So there's a lot of areas that are essentially dark to us that we can't see because there's no sediment available. There's no fossils deposited of that time. We all recognize this challenge, those of us who are in the world of paleoanthropology. Nonetheless, we've done a pretty good job. And here I'm showing, over the last 8 million years here on the y-axis, many of the hominin species that have been discovered and described. Some of their photos are here. Our lineage, the genus Homo, is here. Okay, this is Paranthropus, who I'm going to talk a little bit more about and dive deep. I'll introduce you to Paranthropus a little more deeply. But the name itself of that genus means alongside man. And that's because after the split of the Australopithecines, this is like Lucy, who turned 50 this year, there's basically two branches, we think. It's how we describe the incomplete fossil record. And one is going through Paranthropus here, so these two. And the other is the journey of Homo, starting with these early species, habilis, ergaster, erectus, etc. And here's us at the top. And I think to understand our adaptability, it's useful to have something to compare to. So Paranthropus is our foil for the evening. So here's a Homo sapiens skeleton, and next to it, Paranthropus boisei. And you can see the differences. Homo sapiens are taller. We have longer limbs. We have a more sort of cylindrical rib cage. Paranthropus had this sort of flared or bell-shaped ridge, a larger gut. And then there's height, and then head. We have larger brains. And that's what this data on the other side are showing. This is the last 3 million years of geologic time. And each one of these data points is an estimate of brain size, called endocranial volume, in cubic centimeters. So for the archaic hominins down here, something under 400 cc, so it's about the size of a beer can. You have a brain the size of a beer can, right? And here's Paranthropus in white, okay, so some increase in brain size over time. And then here's pre-modern Homo, and it's a really remarkable difference in the evolution of brain size through time. Paranthropus sort of tops out under 600, whereas our brains today are something like a liter or so, even bigger, Nalgene-sized bottle or something. One really active region of research is what made our brains so big. And especially given that our guts shrank with respect to other hominins. And we think it has to do with diet and figuring out how to get calorically dense foods, either through cooking or processing foods, pounding to release macronutrients. Okay? So Paranthropus, I won't talk about us because we know enough about us. I'm going to talk about Paranthropus, was a genus that had a very strange or unique craniofacial morphology. And it has a large, flat face with very wide cheeks, zygomatic arch, okay? And part of the reason it had such a large arch was there are huge chewing muscles that came up through here and attached where ours do on the side of our head. And then it had a sagittal crest, which we see today in things like carnivores, some primates like gorillas, that's there to actually anchor more muscle. So huge, huge chewing muscles, okay? So if you saw Homo erectus walking down the street, you might walk by and just glance. If you saw Paranthropus walking down the street, you would like do a double take and turn around. It's a very strange looking hominin. There's more to it though. It's known as one of the robust hominins, not only because of its facial structure and all the like large bony elements of the skull, but also the teeth. It has massive molars. So these are the M1, M2, M3, the wisdom tooth here. And even its premolars, which are the two just behind the canine, were absolutely massive, inflated. So it creates this huge chewing surface. The enamel is thick. So just as a comparison, look at your thumb, okay? And then put your pinky next to it. So the surface area of your thumb is about the size of one of these Paranthropus teeth on the surface. And the pinky is about the size of your molar. This is better than asking your neighbor to look in their mouth. So very different dental morphologies, different craniofacial architecture, okay? And Paranthropus was first discovered at Olduvai Gorge, but the oldest one actually comes from southern Ethiopia, a region called the Homo. It's about 2.6 million years old. And then there's another species, Paranthropus boisei, something like 2.3 to 1.2 million years, although recently older have been found. So Paranthropus was around about 1.3 million years. Early estimates of diet from Leakey were that it was carnivorous, okay, these massive thick teeth. Later, people suggested it was a hard object feeder, like huge chewing surface, thick enamel, so it was called nutcracker man. And later, when we looked at the chemistry of the diet, we found that it was, in fact, not cracking nuts at all, and probably not carnivorous. So how do we study diet? There's a couple ways. Traditionally, you look at tooth shape or morphology, and that evolves over tens to 100,000, millions of years. It's sort of the macroevolutionary perspective. And that tells you what the organism evolved or was able to eat. But I'm going to dive into the chemistry of teeth a little bit, because that tells us what the organism actually ate. And here's a Paranthropus jaw again. Here's a dime for scale, these huge teeth. And here's just a smaller colobus monkey tooth showing the variation in primate teeth. And we can study teeth over all different time scales. Choose your y-axis. Scientifically minded people might like it in orders of magnitude. But really, we can study diet over seconds, minutes, hours, all the way to millions of years. And this particular isotope technique that I'll talk about looks at diet over the time the tooth was forming, which is generally months to years. Okay, so how do we do this? Well, in this case, we went to the National Museum of Ethiopia in Addis. This is my team here. It's our taxi driver who, in this old Soviet Lada, would drive us to and from the hotel every day at an arranged time, and we all prayed to whoever this was hanging from the rearview mirror. And over the, as I mentioned, many, many decades of collecting fossils in southern Ethiopia, there are literally hundreds of teeth for us to sample. So we go with our little visors and our notebooks and our drills and collect a small amount of powder from these fossil teeth. We don't work on complete teeth, we often work on broken teeth. So this is the enamel here, and inside the whiter part, or the lighter part, is dentine. Because many paleontologists use the top part, the occlusal morphology, for understanding what species it is, or you can even look at sort of this Last Supper effect up there and looking at scratches and pits and things. We're interested in sampling the enamel, and we take a small amount of powder, 3, 4, 5 milligrams, and take it back to the lab. And there we measure the carbon isotope ratio of it, and that really just tells us if it was an organism that was eating C3 plants, which is a type of photosynthesis that all trees, some grasses, and many woody plants use, or, at least in this part of the world, using C4 photosynthesis. Okay, and that's all grasses, and some of them have underground storage organs like tubers or corms. Okay, and so just by measuring, putting this powder here in a mass spectrometer, we can say if an organism was relying on these C3 foods, which includes, fruits, seeds, nuts, and things, or more grass-based diet. It can't tell us if it was a carnivore. It doesn't give us trophic level, but we know C3 versus C4. And that's really quite informative. And so now we're going to zoom into northern Kenya, the Turkana Basin. And this is Lake Turkana, made famous largely by the early work of Richard Leakey and later his partner Meave Leakey. And here's where we find thousands and thousands of hominin fossils, as well as tens of thousands of other vertebrate fossils. It really is the place where the story of us, I think, is best recorded. And around the lake, we have various strips of, these are where the lamppost lights the fossil record for us, okay, these blobs. And there we can go find fossils and measure them. So about 10 years ago, we measured isotopes in all the hominin teeth that they would let us in the National Museum of Kenya. And this is the story they told. So this is time, the last 4 million years on the x-axis. And this is that carbon isotope ratio. The number doesn't matter. This is a C3 diet down here at the tree, and this is a C4 grassy-based diet up here. So the earliest Australopithecines from the Turkana Basin had a pretty restricted C3 diet. We don't know exactly what it was, but we know that it came from woody vegetation. And then we move along to this other genus, Paranthropus platyops, and we see this huge explosion in dietary breadth. Okay, they go from, this very narrow range to a wide-ranging diet. And then this is the last of Paranthropus, and then we see now Homo in the blue diamond and Paranthropus in the purple circle. And there's different species within them. You can look at the details here, but this is Paranthropus and this is Homo. We were missing a lot of data in here because from these two areas of the basin, we don't have a lot of sediments here. The lamp goes a little dark. And the main thing is we saw that they basically split in their dietary niche. Like Paranthropus is up here, mostly focusing on C4-based foods. And Homo, not only does it have a wider diet, but it's much more flexible in this sort of C3 mixed feeding and C4 space. Okay, so that's giving us already some indication of our adaptability. So as I mentioned, we went to the museum in Ethiopia. Here are those data, okay? And when we put it all together, it's a cloud, it's messy. But what I want to highlight is that, again, we see early on, for the first time, that Paranthropus did actually have a pretty wide-ranging diet, but at some point, based on the available data, has sort of committed to having this pretty narrow C4 range diet, grass-based, whereas Homo remains quite broad and flexible or adaptable. So this is some of the best evidence I think we have that humans have always been adaptable, particularly in our diet. Paranthropus goes extinct sometime around here. I think the last one's around 1.2 million years. And we don't know exactly why, but I will posit that it's likely due to its quite restricted diet. So as climate is fluctuating, and you're a dietary specialist, if your menu item goes away, what are you to do? If you're Homo and you have a wide-ranging diet that's flexible and adaptable, you can likely ride that out. So Paranthropus, in the end, got there 1.3 million years as a species, or maybe as a genus if we stretch a little bit. But what about us? We are 300,000 years on Earth. We should have maybe 1 million years to go if we want to be average. But for us to get there, in the face of climate change, we will need to return to the hallmark of our species. We must adapt, as well as innovate and mitigate climate change. And we need to do it now. This means changing how we sustain our large energy appetites. Can't be fossil fuels anymore. And we need smaller appetites. We have to adapt in how we produce our energy, which means more solar, wind, renewables, and less fossil fuel. And if we do that, we might get to keep our heated toilet seat. This is the climate stripes for the last 150, 200 years. And I'm just showing an example from my own family. So my parents were born between 46 and 52, so I put a little, parent here as a baby. And, came of middle age in the 80s. And they're now happily retired. I was born at the end of Gen X and now carry a briefcase to work. Not really. But, the rest of my life is going to be in the red zone, right? And then there's my son who's here tonight. And he was born here, already in this rapidly changing climate. And the rest of his life will be in this warming world. Anthropogenic climate change is the greatest challenge our species has faced. But you know what else is anthropogenic, I think, is the self-deception that we can't solve it, and for many of us, for me sometimes, the despair around the issue. And I would argue that we need to sort of draw on our collective imagination, develop a united belief that we can solve this, and channel our efforts in a direction that ensures our survival as a species. By my count, we've got at least another 1 million years on this planet, but we're going to have to work for it. We're no longer unfettered in how we live our lives. And this challenge is one that, we're doing not for the older generations, but for us and for our kids. And I think we need to think about who gets the power to make the decisions for our future, right? Because the financial center of the world, the wealth is tied up in essentially the baby boomer generation. They accumulate a lot of wealth, as well as corporations. A lot of the decision-making power is in my generation now, Gen X, and still the baby boomers. Millennials are coming up as well. But the people who will suffer the most are the generations that are in school today and have not yet been born. And I think there's additional people we need to bring to the table that have been traditionally left out. And this goes for the field I'm in of earth science and paleoanthropology. And so there's a large movement to increase diversity in all STEM fields, but this quote here from my former colleague, Koeheli Dutt, sums it up and points the finger at earth sciences for having quite low diversity. So 90% of PhDs go to white people. So we're working on changing that. And one of the things my group does is we have a major effort to train African scientists who have for many years just been left out of the debate or not had a seat at the table. So we've been working with Turkana University College as a master's program, and our goal is to get them from their undergraduate programs in universities in East Africa, which don't quite prepare them for graduate schools here, into a focused master's program on human evolutionary biology, where they can then make the jump and apply to PhD programs in Europe and the US. And to date, I think of the 9 students, 6 who wanted to go to grad school are all in programs, PhD programs in the US or Europe. And so we train them in things in the museum, like drilling teeth. We do some water isotope work as well to study past climates, and to do that we study modern plants and soils. We make these rain bucket collectors and do a lot of research collection work at the museum. We also need to build capacity in Africa so that they have the laboratories, the facilities, and the means to make the measurements, so they're not beholden to the labs at Harvard or wherever, okay? And so to that end, we built the first stable isotope for teaching and training in East Africa. We just do water isotopes, that's what that instrument does, but we're expanding to do other types. And it's not just for paleoanthropology or paleontology, fossil teeth. We can measure isotopes in many things, and it has a huge range of applications to hydrology, ecology, forensics, many different fields. And then we need to teach students, not just here in the US, but abroad. And so I've been teaching classes abroad in East Africa, granted through Ivy League schools. But this has been a model for us so that now we can start bringing in Kenyan students and students from other African countries to participate in these high-intensity short courses where we study geochemistry, ecology, etc. So with that, I'll close, and thank you for listening.